So here we go with our second lesson on logarithms. Some of this is going to be a little bit of a duplicate of what we just talked about. This specifically right here is going to kind of duplicate what we just said, so I'm going to go through it pretty quick. Logarithm is an inverse of an exponential function. And remember we said the big deal, the reason a logarithm is so important is it allows you to solve for a missing exponent. You just got an activity that was all about this, converting from logarithmic to exponential form and vice versa. Just remember that in both forms you have a base. Okay, so these are called the base in both forms. And then the exponent is the answer to the logarithm. Okay. So again, just clarifying that difference. Hopefully the examples that you just worked through went pretty well. So there's a couple of different kinds of logs that come up more often than others. And again, some of this stuff right now is going to seem like, why on earth would we need to do that? And in Algebra 1, we really just scraped the surface of logarithms. We really just start to learn the very basics so that when you get to Algebra 2 next year, you're a little bit familiar with them. But we're probably not going to do enough with it this year to where you're going to see what it's really used for, what's really useful about it. So try not to let that get to you. Try not to get discouraged because you're thinking, gosh, all I'm doing is rearranging these numbers, okay? One of the logs that comes up a lot is what's called a common log. And a common log is a logarithm with a base of 10. So ordinarily it would look like this. Log base 10 of, 100, something like that. However, because common logs happen so often, when it's a common log, we don't write the base. We just leave it out, okay? And if there's no base, you assume that it's a 10. If it's a base other than 10, you have to write the base there. So it's kind of like, we talked about when you have a square root, we don't write the 2 on the outside, but we assume that it's there. Or when we have an x, we don't write the 1 in front of it, but we assume that it's there. With a logarithm, if there's no base written, we assume that it's a base of 10 because we assume it's a common log. The other log that you're going to see fairly often is what's called a natural log. And a natural log is a logarithm with a base of e. That's that same e from the PERT formula and the continuous growth formula. So a logarithm with a base of e is called a natural log. Oh, sorry, this part is just what I just said a second ago. I forgot that was going to pop up here. But if it's shown without a base, it's automatically considered to be a common log. And then also you should know that natural log is abbreviated ln. So these two logs are the ones you can find on your calculator. Natural log is the ln button, and you know where the ln button is because it's what you use to find the e to the x. So look at your calculator right now, okay, and you should find down on the lower left-hand side a button that says ln. Somewhere near that, probably right above that, should be a button that just says log. That is a common log button, okay? So your calculator is not designed to do all of the logarithms for you, and we're going to talk about ways to get around that later on, but it does do common logs for you. So let's just practice typing a couple of these into our calculator. The first one, log of 100. Again, that's just the log button on your calculator, so type in log of 100. Should get an answer of 2. Okay? And remember, there's really like an imaginary 10 here, so what you're saying is 10 to the power of 2 equals 100. Now let's think about log of 42. Log of 42 is saying 10 to some power equals 42. And I know this one's going to be a weird one because there's no, nice, happy whole number power that's going to turn a 10 into a 42. Should be 1.62 when you type it into a calculator, which we knew it was going to be less than 2 because when you do 10 to the power 2, you get 100. Okay, and this is less than 100. Okay, log of 0.001 should be -3. So again, you should be getting these just from typing them straight into your calculator. Find the log button on your calculator. If you can't find it, ask somebody around you. These ones we're going to try typing in with the ln button. That's the natural log. Okay, so you are asking yourself, e to what power gives me 16? And remember, e is that crazy like 2.718 da-da-da-da-da number. Okay, but you don't have to know that to do the problem. You just have to type in ln of 16. Comes out to be like 2.77. How about natural log of 402? Comes out to be 6.00. Notice I wrote those zeros in there. I know that technically that would round to pretty close to 6, but I put the zeros in there to show that it's not exactly 6, that there is some decimal component to it. And the natural log of 1 is 0. That one might seem a little weird, but remember what you're really saying there is your base, e, to the power of 0 is equal to 1. And anything to the power of 0 is equal to 1. Okay, this is really the bulk of this lesson, and this is what your homework assignment is about tonight. Remember that logarithms are really exponents, okay? And we learned a whole bunch of rules about exponents. Like, for example, when you multiply two powers, you end up adding the exponents, okay? So logarithms kind of work backwards. Well, I guess not really backwards, but if you take the log of two things that are being multiplied together, okay, if you take the log of something times something else, you can separate that with addition. So you can make it, you can find the log of x and add it to the log of y. Okay? And it's because of this. Okay? The fact that multiplication with exponents, if you multiply with powers, you end up adding the exponents together. Well, these logs are actually exponents, and you add exponents when you multiply. So the multiplication property says that if you have a log of two things multiplied together, you can separate that and do the log of the first and add it to the log of the second. Okay? Similarly, the division property says that if you have the log of two things being divided, you can separate that with subtraction. Because remember, the division property of exponents is that when you divide powers, you subtract the exponents. And the power property says that if you take the log of x to some power, you can move that power down in front and multiply. Because remember, when you raise a power to a power, you multiply. Okay, so powers become multiplication. This would become n times the log of x. These might not seem like a big deal right now. They're going to get to be very useful to you. So right now it is going to feel like you're just, taking things apart and putting them back together. Because I'm going to be asking you questions where I give you this and I want you to write it like this. And I'm going to be giving you questions where I give you this and want you to write it like this. Okay, so right now it's going to feel like you're just moving things around. But I promise there's a reason that it's important to know how to do that. Okay, so for example, this says to simplify and write as a single log. So I'm combining things here. Okay, so if you think back to that last slide, I'm just going to write down, for example, the multiplication property that we had on the last slide. You don't have to write it again. It's probably on your paper right in front of you. But log of x times y equals log of x plus log of y. Okay, that was our multiplication property that you wrote down just a second ago. This right here is a single log, and this is multiple logs. So these examples are giving us the multiple log version and wanting us to combine them. But remember that addition really becomes multiplication. Subtraction would really become division. Okay? So this right here tells me that I'm going to combine this piece and this piece with multiplication, because addition, when you're adding exponents, it's because you're multiplying the powers together. Okay. By the way, the 5s down there, those are just your bases. That's just to show you that these two things have the same base. If they didn't have the same base, you couldn't combine them. So when I go to write this, I'm going to write it as a log base 5. I'm going to keep the base exactly the same. And I'm going to combine the 3 and the x with multiplication. That's how I would write it as a single log. So addition becomes multiplication. Okay, let's look at this next one. This 4 out front. Remember the power property, the last one we wrote down, said that you could take the power and slide it down in the front with multiplication. So I'm going to put it back. Okay, I'm going to put it here. I'm going to make it 3 to the 4th power. And then, because this is subtraction, I'm going to combine this piece and this piece with division, because subtraction turns into division. So this would be log base 2 of 3 to the 4th divided by 3. Okay. Now you could actually figure out what that's equal to. Let's see. I believe it's going to come out to be 27. So if you just type this piece into your calculator, you would get 27. So I would write this as log base 2 of 27. Okay. All right, next one, kind of a long chain. First of all, if I have numbers out in front, I'm going to slide those up here and make those exponents, okay, because the multiplication came from exponents. And then, so now I don't have this 3 to worry about, I don't have this 2 to worry about. Where I have addition, that's going to become multiplication, so I'm going to multiply these two. And then where I have subtraction, that's going to become division. So my final answer is going to look like this. Log of x to the 3rd times, oh, I made a mistake here. Threw me off for a second. This should have really been a 2 because this down here was a 2. Times y to the 2nd divided by z. So my parentheses should really go around that whole thing. Okay, so the numbers out in front, I turn them back into exponents, okay, and then I combined here with multiplication because of that addition, and I combined here with division because of that subtraction. So this is how I would write my final answer. Natural logs work the same way. That's what these are down here, ln and ln. All of those same properties hold. So this 4 is going to become an exponent of 4. This 5 is going to become an exponent of 5. And then because this is addition, I'm going to combine these two with multiplication. So I would write this as natural log of x to the 4th times 3 to the 5th. And the only other thing I might do with that one is, because you can actually calculate 3 to the 5th. Well, maybe you can. I don't have a calculator in front of me. Let's see. It's going to be 9 times 27. So 243. So this piece right here is equal to 243. So I might write this as ln of 243 x to the 4th. Okay. At this point in the game, honestly, if you would just left that as 3 to the 5th, I would have been fine with that. I really just want to make sure that you are seeing how these numbers are supposed to combine. Okay, let's try the next one. Okay, in this set of slides, we're going the other way. Okay, we're taking a single log and writing it out as multiple logs. So we're separating it into smaller pieces. So, just a little bigger here. In this first problem, I really have two things that I'm dealing with. I have a 5 and I have an m. So each one of those things is going to get their own log, okay? And because this right here is multiplication, when I write that like that, 5 times m, I'm going to turn that into addition. So I'm going to say log base 4 of 5, log base 4 of m. So that's really just separating the two pieces. And then because that's multiplication, I'm going to combine them with addition. Okay, let's try the next one. So the first thing I'm going to do is take my two pieces, the 16 and the x squared. I'm going to give each one their own log. So log base 2 of 16, log base 2 of x squared. So this base of 2 just stayed the same in both of those. Okay, now this right here is multiplication. So I'm combining these with addition. And then there's one more thing I can move around. This exponent, using that powers property, I can put down in front. So my final answer should look like this. Log base 2 of 16 plus 2 log base 2 of x. Okay, so slide the exponents down in front. Okay, number 3. On this one, I have 1, 2, 3, 4 different pieces that I'm working with. And it's a natural log, so each one's going to get its own natural log. Natural log of 3, natural log of x to the 4th, natural log of y to the 3rd, and natural log of z squared. Okay. The 3, the x to the 4th, and the y to the 3rd, all of those are combined with multiplication. So when I separate them, that multiplication is going to turn into addition. That lonely z is separated from everybody else with division. So over here, that's going to become a subtraction. Okay, so the z is going to end up getting attached with subtraction. Give you a minute to write that down if you need it. And then step 2, I'm going to take all these exponents and put them down in front. Okay, so this would become ln of 3 plus 4 ln of x plus 3 ln of y minus 2 ln of z. And that's what your final answer would look like for that one. Okay, and one more. Log of x over 3 squared. Okay, for this one, remember that when you raise a fraction to an exponent, that exponent really goes on the top and the bottom of the fraction. So I would go ahead and put it in both places to begin with and just ignore the one on the outside. Then I would say, all right, well, I have an x squared and I have a 3 squared. Each one of those gets its own common log. So log of x squared, log of 3 squared. They're separated in the problem with division, so that's going to be subtraction over here. And then let's shift my exponents down. So that 2 is going to come down here, that 2 is going to come down here, and I'm going to get 2 times the log of x minus 2 times the log of 3. I'm going to pull that whole page back down and just give you a minute. If there's any of those that you're confused on, feel free to ask questions. Or if there's any of those you just want to make a note on or you want to look at again, just take a second and digest. Okay, one more quick little thing. Let's see if we understand what logs are really asking us for, okay? I want you to try to do these without a calculator. Don't touch a calculator here. Some of them a calculator is not going to help you anyway. So when I say, what is log base 5 of 5? Well, remember, when I ask you what is that equal to, really what I want to know is what exponent. So what is the exponent that turns this 5 into this 5? Well, 5 to what power gives you 5? It'd be 1. Okay, so anytime you have a log with the same base as the number up above it, okay, and I don't know what the name of this number is, but anytime these two numbers match, it's going to be a 1 because it's going to be this to the power of 1 gives you this, okay? Similarly, if you look over here at ln of e, remember your natural log base is e. Okay, so this is really the same thing as what we had going on over here. This is saying e to what power equals e? Well, again, that'd be 1. Okay. On this next one we sort of talked about earlier. What is log of any base, log with any base of 1? Well, what I'm really saying to you here is b to what power is 1? Well, what power gives you 1? It'd be 0. Okay, anything to the power of 0 is equal to 1. So it doesn't even matter what this base is. Anything to the power of 0 is equal to 1. So anytime this number is a 1, your answer is a 0. Doesn't even matter what your base is. So going over here to this other one, ln of 1, well, that's just the same thing with a base of e. So I'm saying e to what power is equal to 1? Oh, I did it again. E to what power is equal to 1? Well, that's the same question, okay? Anything to the power of 0 is 1, so your answer here is still 0. Anytime this is a 1, your answer is going to be 0. I don't care what your base is or what kind of log it is. Okay. B to what power equals 0 then? How do you raise something to a power and get it to be equal to 0? Well, that's easy. You don't. That's impossible. You remember we talked about, like, when we did exponential functions, that the graph never touches the x-axis because it can never equal 0? That's what this is saying. Okay, this is saying that I'm taking b and raising it to some power and making it equal 0. That can never happen. Okay, so this number is a 0, never going to fly. Always going to be no solution. What about over here? Remember, when it doesn't have a base, it's really a base of 10. So this is saying 10 to what power is equal to negative 2? Well, what power can you raise something to that would make it turn from positive to negative? Okay, the answer is there is none. Even if you raise it to negative powers, even if you did like 10 to the power of negative, I don't know, 5, remember a negative power is just going to make it be 1 over some big number. Okay, but it's never going to turn it negative. So just like it's impossible for it to equal 0, it's also impossible for it to be a negative. So the number in this position always has to be positive. It can't be 0 and it can't be negative. Okay, if you end up with something like that, no solution. Okay, you have a homework assignment that pretty much focuses just on the last 2 slides. So not this slide, okay, that I'm looking at right now, but the 2 slides just before this, the separating the logs and the putting them back together. Okay, so use that for reference. That is your homework assignment tonight, and you're going to practice with this more tomorrow, and we will go over all of this on Monday.